Okay, so Unit 9, we are starting acids and bases. So here are just some general properties, the difference between acids and bases. So acids have a sour taste, where bases have a more bitter taste. So you can kind of think like cabbage is very bitter, a lot of herbs are very bitter. With sour, think about citrus, so like lemons, etc. Acids corrode metals. They have a pH that is less than 7. They are electrolytes. That just means that they split into their ions when they dissolve in water. They're going to turn blue litmus paper red, and they will produce hydrogen ions in water. So that is a key with acids. With bases, they're going to feel soapy or slippery. So a soap is a base. So if you think about how soap feels between your fingers. pH is greater than 7. They are also electrolytes. They will turn red litmus paper blue, and then they will produce hydroxide ions in water. All right, so let's look at some definitions of acids and bases. So acids are proton donors. So a proton is just a hydrogen ion. And then bases are proton acceptors. Okay, so they're going to accept that hydrogen ion and form a new ion or compound. So here are a few examples. So we have HCl plus water, and that's going to give us H3O plus, and then chloride Cl minus. So this is an acid, so it's going to donate the proton. And if you look, what happens is that hydrogen actually gets donated to that water, that proton. So that makes this the proton acceptor, which is the, base. I was getting ahead of myself there. So acid is the proton donor, base is the proton acceptor. On the opposite side of the equation, now we have what was made after the base accepted that proton. This is called the conjugate acid. Okay. And then we have what's left over when that proton is gone, and now that is the conjugate base. You can look at it as, well, if I look at this substance here, this is more willing to donate a proton than accept another proton. And then this substance here is more likely to accept that proton, so that's why it's the base. All right, let's look at the next example. So if I look here, I have NH3 on the reactant side, and that turns into NH4 plus. So that means that it accepted a hydrogen, a proton. So proton's going to go from water to NH3. So that makes this the acid, and the NH3 is the base. And then after this accepts the hydrogen, what's left over is this, which is our conjugate acid, and our OH minus, which is our conjugate base. Now notice we're forming NH4 plus, that is the ammonium ion. Water is called amphoteric, okay, because it means it can act as an acid or a base. So if we look in this first equation, it acted as a base because it accepted that hydrogen. In this second equation, it acted as an acid because it donated a hydrogen or a proton. All right, so there are different strengths to acids and bases. Strong acids and bases actually dissociate completely. So that means they break up completely into their ions. And weak acids and bases do not. So some examples you might see, so we're going to talk about these later, but we have hydroiodic acid. This is a strong acid. So it will actually break down into hydrogen ions and iodide ions when in water. So these would all be aqueous because they'd be in water. Okay. Another example for a base would be sodium hydroxide. And sodium hydroxide is going to break down into sodium ions and hydroxide ions. And again, all of these are going to be aqueous. For weak acids and bases, we're not going to talk too much about this, but it's going to form something called equilibrium. So there's actually going to be some of the reactants as well as some of the products that are going to be in the solution. So a common one is actually acetic acid. And what we do is we draw a double arrow. This is known for equilibrium. And it will still form hydrogen ions and then the acetate ion. But that double arrow means that I still have some of this in solution. So some of the hydrogen still bonded with the acetate ion. Okay, so here are the strong acids that you need to know. So you need to memorize these strong acids. If it is not one of these strong acids, then that means it is going to be a weak acid. So that makes it life easier. If you know what the strong acids are, everything else is weak. So we have HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3, that is nitric acid, H2SO4, sulfuric acid, and then HClO4, be careful of that oxygen, number of oxygens. This is perchloric acid. All right, and then every other acid we assume is weak. The most common ones that you'll see, HC2H3O2, that's acetic acid. You'll see that one a lot. That's the acid that is actually in vinegar. And then here's an example of another one. So here's formic acid, and then any other organic acid. It'll contain carbon, hydrogen, and oxygen. Okay, let's go over strong bases. So strong bases are group 1 or 2 with metals with hydroxide, except for beryllium. So here are some common ones you'll see most often. So sodium hydroxide, potassium hydroxide, lithium hydroxide, and then barium hydroxide. Again, these are going to be your strong bases, so anything that is not group 1 or 2, except for beryllium, is going to be a weak base. The most common one you'll see is ammonia. So this is a special name for NH3. It is known as ammonia.